Welcome to the 19th lecture on calculus. So in the previous class we have discussed the notion of limit of a function using the notion of sequences of real numbers. Today we will see another definition. We call it epsilon-delta definition, and we will prove that both the definitions are equivalent, and we will also see some examples. A function, the limit of a function, there is a fundamental concept in calculus concerning the behavior of the function near a particular point. So you consider a function f from d to r, where d we call it domain of this function, and this is just a subset of r, and you consider a point c. It should satisfy certain condition. What is that? That d should contain an open interval around c except possibly that point c itself. And in this case we can talk about the limit of this function f at x equal to c. So we say that the function f has a limit, some real number L, as x tends to c, if this function value f of x, it gets closer and closer to this particular value L as x moves closer and closer to c. Consider this function. So this is a function from this collection of all non-zero real numbers to this set of real numbers, and this is given by f of x, it is same as sin x divided by x for all non-zero real numbers x. And then you can see that if x is 1, then this function value it is given by this. If x is 0.1, so this function value it is given by this, and it is getting more closer to 1. And 0.1, then this function value it is given by this, and it is getting more closer to 1. So you can see that as x approaches to 0, then this function value it is approaching to 1, and this is the notion of limit. So in this case we say that this function, though it is not defined at 0, but as x becomes closer and closer to 0, this function value it becomes arbitrarily close to 1, and in this case we say that this function it has a limit 1 as x tends to 0, or we say that this function it has limit at x equal to 0, and that limit value is 1. Okay. So we have given the definition of limit of a function in terms of the sequences of real numbers, but today we will give epsilon delta definition. So we should recall this notation, delta neighborhood. What is delta neighborhood? So you consider a positive real number delta, then the delta neighborhood of a point c in R, it is just this open interval. So it is collection of all these real numbers lying in between c minus delta and c plus delta, excluding these 2 points. Okay. So it is this open interval, that means collection of all real numbers, so that this absolute value, that is the distance between x and c, this absolute value is less than delta. Or it is collection of all real numbers x such that x lies in between c minus delta and c plus delta. And we use this deleted delta neighborhood. So by definition, what is deleted delta neighborhood of a point c? It is just that open interval and excluding that singleton set c. So it is this open interval except this point c. Okay. So it is collection of all real numbers such that 0 less than this absolute value less than delta, or collection of all real numbers x such that x lies in this range but x is not equal to c. So we call this set as deleted delta neighborhood of the point c. We use these two notations in the definition of limit. Okay. So here we prove that both the definitions, one is in terms of the sequences of real numbers and another one is epsilon delta definition, both are equivalent. And then in some book they define the notion of limit in terms of this epsilon delta thing. Okay. So throughout we have this hypothesis. So f is a function from this set d to r, where d is a subset of r and we call it domain of f, and c is some point which satisfies certain condition. What is that? That d should contain a deleted r neighborhood of this point c for some positive real number r. Okay. So d should contain an open interval like this, c minus r, c plus r around c, except possibly that point c itself. So here D may or may not contain the point C. Okay, so D should contain an open interval except possibly this point C for some real positive real number R. Okay, that is the condition, that is the hypothesis we should have, and then we can talk about the limit of this function f at the point C. Okay, so last time we have defined this notion of limit in terms of this thing. So we say that f has a limit L at the point x equal to C if it satisfies this condition. Okay, and today we will prove that this condition, it is equivalent to say this condition. Okay, so with the above hypothesis, for a real number L, the following are equivalent. So first one is saying that for every sequence x suffix n in this set, so here all the terms of this sequence are points of D, and no term of this sequence it can be equal to C. Okay, so and if this sequence converges to C, then this sequence, this function value, this sequence should converge to L. That is the condition. Okay, so for every sequence x suffix n, if it converges to C, then this sequence of this given by this function values that should converge to L. Okay, so this is the first condition, and second one is saying that for every positive real number epsilon, there should be some positive real number delta such that for all x belongs to D and this deleted delta neighborhood of C, this function value should lie in this range, or in other words, for all the points in D which is there in the deleted delta neighborhood, this function value it should lie in this epsilon neighborhood of L. Okay, so in some book they define that the function f has a limit L at x equal to C at this point if it satisfies certain condition. What is that condition? That for every positive real number epsilon, no matter how small it is or how big it is, for every positive real number epsilon, there should be some positive real number delta depending on epsilon, such that for all points x belongs to this D intersection this deleted delta neighborhood of C, this function value it should lie in the epsilon neighborhood of L. So here I should write that this delta it depends on epsilon. So in some book they write delta of epsilon. So it is saying that for every epsilon, for every positive real number epsilon, there should be some positive real number delta depending on epsilon. Okay, so if you vary epsilon, then this delta will vary. So for every epsilon, there should be some delta which satisfies this thing. That is the epsilon delta definition. In this case, we write f of x tends to this particular value L as x tends to C, or we write that limit of f of x as x tends to C, it is same as L. Okay. So first we will analyze two examples using this definition, and then we will prove this theorem that why these two conditions are equivalent. Okay. So last time we have analyzed this example using the definition in terms of sequences of real numbers, but let's analyze this example using this definition, epsilon delta definition. Okay, so you consider this function where this if x is negative real number, then this function value is 1, and if x is 0, then this is given by 2. Okay, so on the negative side it is given by this thing, it is constant thing, and at x equal to 0 it is just 2, and after 0, so if x is greater than 0, then this function value is given by this line. Okay, and now let's verify whether limit exists or not at x equal to 0 for this function. It is 1. So though this function value it is f of 0 is 2, but at x equal to 0 this limit I claim that it is 1. Okay, and then I should verify that this 1 it satisfies this epsilon delta condition. Okay, so you consider an arbitrary positive real number epsilon. So for this epsilon we should find some positive real number delta which satisfies that condition. Okay, so before that I should analyze this distance between f of x and 1. Okay, so this is I should write this is 0 if x is less than 0, and this is x if x is, so we choose delta that is same as epsilon, and then let's try to verify that for this delta whether it satisfies this thing or not. Okay, so our aim was to prove that for every epsilon there exists some delta. Okay, now I am claiming that for this epsilon, if we choose delta that is same as epsilon, then that delta will work. Okay, why? Because you can see that this condition it is equivalent to say that minus delta less than x less than delta. Okay, so if x is negative, lies in between minus delta and 0, then anyway this thing is 0, and if x is positive and that is less than delta, then anyway this thing it is same as x, and since x is less than delta, so x is less than epsilon, right? So because delta you are choosing, it is same as epsilon. So in this way we are proving that for every epsilon there exists some delta which satisfies this thing. So this 1 it is satisfying epsilon delta condition. So 1 is the limit of this function f of x at x equal to 0. Now let's consider this point, so x equal to 2. Okay, so at x equal to 2, what should be the limit of this function? I claim that at x equal to 2, the limit of this function it is same as 3. So let's try to verify that this 3 it satisfies this epsilon delta condition, and from this picture let's try to understand what is this epsilon delta condition actually. So this definition is saying that we say that f has a limit L at x equal to c if for every epsilon there exists delta such that this thing holds true. For every epsilon neighborhood there should be some delta neighborhood, so that for all the points in that deleted delta neighborhood this function value it should lie in this range greater than 0. For this epsilon I should find delta. So before that let's try to analyze what is this distance of x. Here it is given by x plus 1, so it is x plus 1 minus 3, so x minus 2. Epsilon, if you choose delta that is same as epsilon, then that delta will work. Okay, and next we will analyze another example. So it is just this function from D to R, where D is collection of all non-zero real numbers, and this f of x it is given by minus 1 for all negative x, and for all positive x it is given by 1. Okay, so on the positive side it is given by this thing, and on the negative side it is given by minus 1. Okay, and in this case I claim that f of x does not have a limit at x equal to 0, or in other words limit extends to 0, f of x does not exist. F of x at x equal to c it exists for any point c not equal to 0. Okay, so let's first consider this point x equal to 0. Okay, and so in this case, so if we see that we have two equivalent definitions, though we have not proved that, but using the definition of limit in terms of sequences, we can argue that why limit does not exist at x equal to 0 for this function. Because if you consider a sequence which approaches to 0 from the positive side, then this function value it is approaching to 1, and if you consider a sequence which approaches to 0 from the negative side, then this function value it is approaching to minus 1. So in this case it is not satisfying that first condition. Okay, the definition in terms of sequences of real numbers. So here also we can see that at x equal to 0 it is not satisfying the epsilon delta condition also. Okay, so we can prove that, so you have to prove that this limit does not exist. So whatever L you choose, it does not satisfy that epsilon delta condition at x equal to 0 exist. Okay, so basically we are proving that there does not exist a real number L which satisfies this condition, this epsilon delta thing, for the function f of x, this function at x equal to 0. So you consider epsilon, that is half, 1 by 2. Okay. So for this epsilon, if you can prove that there does not exist delta such that which satisfies this condition, then you are done. Okay. So suppose L is somewhere here. Okay. So then what is your epsilon neighborhood of L? So if you consider epsilon, that is half, so your epsilon neighborhood, that will be this one. Okay. So we should find a delta neighborhood of 0, okay, such that for all the points in this delta neighborhood, that function value, it should lie in this range. But you can see that no matter, so whatever delta you choose, it is not satisfying this condition, right? So because see, so if you consider this delta neighborhood, so you can see that for all the negative points, negative real numbers in this delta neighborhood, so this function value is -1. So of course it is not lying in this epsilon neighborhood. And if x is positive, it is function value is 1, so that is also not lying here. So L, it can be anything, but you can prove that no matter whatever L you choose, that it is not satisfying this epsilon delta condition. Next we will prove that these two conditions are equivalent. Okay. So you consider a function f from D to R, D is the domain, and C is some point, okay, in R, and it should satisfy the condition that D should contain an open interval around C except possibly the point C. Okay. So with this hypothesis we will prove that these two conditions are equivalent, okay, for this real number L. Okay. So you start with this real number L, and first condition, it is saying that for every sequence x suffix n in this set, so all the terms are points of D and no term of this sequence is equal to C. Okay. So in this case, if your sequence converges to C, then this function value f of xn, it converges to L. So that is condition 1. And condition 2 is saying that for every epsilon there should be some delta which satisfies this thing. First prove 1 implies 2. So you have this condition 1, and then we should prove that condition 2 holds true. Okay. So if possible, suppose that for a particular epsilon there does not exist delta which satisfies this condition. So we prove this implication by contrapositive way. So it is equivalent to say that for every delta there exists a point x delta in this domain such that x delta is there in the delta neighborhood, deleted delta neighborhood, but this function value, it is not there in the epsilon neighborhood of L. Because if we are assuming that for this particular epsilon there does not exist delta satisfying this condition. So whatever delta you choose for delta, for this delta, you can always have a point which is there in this set, but it is not satisfying this condition. So what I mean, that for this delta, for every delta you can have a point depending on that delta. So that is why we denote in this way x suffix delta. So it is there in this set, so that means it is a point of this domain, and this point, it is there in the delta, deleted delta neighborhood of C, but this function value f of x delta, it is not there in the epsilon neighborhood of L, or in other words this distance, it is greater than or equal to epsilon. Okay. And then for every natural number n, you just consider your delta is 1 by n. So from this condition now you can see that if you chose delta is 1 by n, then of course for this delta also you can have some point, and let me denote that point by x suffix n, okay, which is there in D and which satisfies this condition, but that function value it is not there in the epsilon neighborhood of L. So in other words, for delta equal to 1 by n, there exists a point which is there in D and which is also there in the neighborhood deleted 1 by n neighborhood of C, but this function value f of x xn it is not there in the epsilon neighborhood of L, or in other words this distance it is greater than or equal to epsilon. And thus we obtain a sequence where all the terms of this sequence are there in this set. So these are points of D, and but no term is equal to C, and this limit of xn that should be C. So because we have this inequality, and then if you use sandwich theorem, so limit of this absolute value that should be 0, and from there you can conclude that limit of xn that should be C. And what should be the limit of f of xn then? So for this sequence, since we have this inequality, so if you apply limit here, so limit of this thing that should be greater than or equal to this epsilon, okay. So limit of this thing it cannot be same as L, because if this limit is same as L, then limit of this thing that should be 0, okay. So that means 0 should be greater than or equal to epsilon. That is not possible. So this contradicts the assumption that limit n tends to infinity f of xn is L, okay. So that was your condition 1, right. So here we are proving 1 implies 2. So we are proving it by contrapositive way. So if possible we assume that 2 is not true, okay, and then we are contradicting the condition 1, okay. And next we should prove 2 implies 1, okay. So 2 is saying that for every epsilon there exists delta such that for all points in D which is there in the deleted delta neighborhood of C, this function value it is there in the epsilon neighborhood of L. So suppose you have this condition, and then so we want to prove condition 1 and condition 2 is given, okay. So to prove condition 1, you just consider a sequence in this set, okay, such that this limit is C. So you consider a sequence in this set whose limit is C, and next we want to prove this thing, okay, to show limit n tends to infinity f of xn, that is L. So this we consider an arbitrary positive real number epsilon, and then we should prove that this L it satisfies epsilon n condition, okay. So for this epsilon we should prove that there exists a natural number certain stage, so that after that stage the distance between this term and L that is less than epsilon. So that we want to prove here. So condition 2 is given and we should use that, okay. So by the condition 2, for this epsilon there exists a positive real number delta which satisfies that condition, this one, and then you use this thing. So since C is the limit of xn, so for every positive real number there exists certain stage, so that after that stage the distance between nth term and C that is less than that particular positive real number, okay. So since C is the limit of xn, so for this positive real number delta there exists a natural number n such that beyond that natural number all the terms satisfy this thing. So the distance between nth term and C that should be less than delta for all natural numbers beyond this big N, okay. And it follows that this distance then that should be less than epsilon. Why? Because we have this condition, okay. So if some point it is there in D and it satisfies this thing, then this function value it should satisfy this one. Okay, but if we consider all natural numbers, so for every natural number beyond this big N, if you consider this point x suffix n, so it satisfies this thing. So x suffix n, this is a point of D, and so it is not equal to C, and so you have this inequality. So that means x suffix n, it is satisfying this condition. So f of xn, it should satisfy this condition. Okay, so the distance between f of xn minus L, that should be less than epsilon for all natural numbers beyond this big N. So ultimately we are proving that for this epsilon there exists a natural number, so that beyond that natural number the distance between f of xn and L, that is less than epsilon. So we are proving that L is satisfying the epsilon n condition for this sequence. So thus limit n tends to infinity f of xn is L. So assuming condition 2, we are proving condition 1. Okay, so we are proving that for every sequence in this set whose limit is C, the limit of f of xn, that should be L. Okay, and this completes the proof of this theorem, and that's all. I'll stop now.